questions 1 and 8 on the sheet, just want to look in to and consider what you know about the perfect square. Yeah? Assuming you did, yeah. Than any of the other bits. Yeah. Okay. But I'll just take a quick look at it, and then. So if we can write something like this, s plus 2 squared, that's called a perfect square. Yeah. Now, if we take what that's written out as, if we multiply out the brackets there, because that's effectively what that is, 2s plus 2's, we get s squared plus 4s plus 4, a quadratic. Yep. Okay. Equally, s plus 4 all squared is s squared plus what? 8s plus 16. Can you see how this number there is always in there? Yeah. And what's this number? Yeah. All right. So we can say s plus a all squared, a general solution is that we get s squared plus 2a plus a squared. Yes, sorry. Well done, Steffi. Alright, everybody happy with that? Now, on the other side of the coin, because what we're going to be wanting to do is go from a expression as a quadratic to a perfect square. So go the other way. Turn a quadratic like this, which we would normally say is equal to 0, into a perfect square. Yeah? So if we take s squared plus 12s plus 36 is equal to 0, how do we write that as a perfect square? I want to know how you get that, Seppi. You divide that by 2. Yeah, so we go on the other way. Add that by 2 and put it in there. Yeah. And if you look at that, it's the square root of the 36. Yeah. And those two are the same. So those of you that are here have a reasonable understanding of the perfect square by the look of it. Alright. The only thing we need to consider is oh, I don't know, I ain't got a clue. This is just something I found from a long time ago. You might have had it. Yeah, you have. So, question 1 in the practice question sheet. It says we've got a step input, 50 volts. Always worthwhile drawing a diagram. You're likely to be asked to draw one in the exam anyway. Inductor of resistance 0.5 ohms. And 200 millihenries is connected in series with a capacitor of 500 microfarads. Like so. And when we turn it on, we get current flow, and we use Laplace transforms to determine an expression for the current during the transient period. Okay? So, first thing we can do is say that Vs is 50 over S. Yeah. Zs is so R plus Ls. It's good to show that you know one of us. That's the formula, and then write the answer in. 0.5, 0.2 S plus you know that avoiding fives never works. One over 0.305 S. Yeah. Everybody happy with that so far? Okay. Now, what we need to do is write that as one fraction. So, how do we do that? We multiply by i.e. we multiply it by 1 effectively, but we're multiplying it by multiply these two bits by that. Yeah. So we end up with initially Zs is equal to 0.43025 S over 0.305 S plus S squared over 0.305 S plus R1. Alright? Now, I've done that step, intermediate step. You won't necessarily, once you get used to it, do all of that, because this is how we want to write it. We want to write all over 0.005 s. That'll be 2.5 s plus 0.0001 s squared plus 1 on the end. So there's our final expression for the impedance, written as a single fraction. Anyone disagree with any of them numbers? You could do, possibly, but there ain't no need to do it at this stage. Yeah. Alright. No need. I certainly haven't got that in my solution anyway. Alright. Maybe. You can do it in one or more places. I think after you have included the voltage and got everything tied together, might be a more appropriate place. Alright? As long as you get the right answer in the end, you know, that ain't going to really make too much difference. Alright? So what we move on to now is we can write that IS is equal to 50 over S all over that bit. And that's all over 0.305 S. Yeah. So now we go into that, we got a fraction divided by a fraction mode. Guys, please. So we're 50 over S multiplied by, and then we turn this other fraction upside down. So we put the 0.305S on top. I copied it, pasted it really, didn't I? Yeah. And then we bring them together, like we say. So 50 times 0.005S. Let's just put this in there. That becomes we'll put all the S's in to start with, and there's some cancelling that will happen. And then we have agree with that? Yep. And then what happens is, I'll do it in green, that cancels, squared cancels there, and that becomes a 2, and that goes to 1. Yep. And I've gone, in the solutions that I'll give you anyway, I've gone straight from that to that. As you get to know, that always happens, and you just do it, alright? So we got 0.025 over 0.3025 s plus 0.301 f squared plus 1. Now we get s squared on its own. So you can see now it won't really matter whether you did it before or after. Yeah. And the result of that is $250 Everyone agree with that? Yeah? Yeah. Yeah. And what we've got is this denominator is in that form if we move the s squared around a bit, e.g. Yeah. So we got a quadratic squared term, an s squared term, where I is 1, yeah. B is 2.5, and the constant is 10,000. We need to write that as a perfect square. So we do, how do we do that? Yeah. We do B over 2, which is 2.5 over 2, 1.25. Yeah. And then the remainder is which is yeah. Therefore, IS is equal to, going back to our original expression, 250 over S plus 1.25 all squared plus 9998.44. in the table does this look like? Yeah, but just read the expression out for me, Jake. I omega. In the table. Yep. We've got a constant. That's a constant. Remember what omega is? That's the frequency in radians per second. Okay. We've got a constant in here for B. Okay. And we've got a value for omega squared. That's B. And that is A omega. Yeah, we got all them parts. Therefore, what we need to do is turn those parts that we've got into the constants to find A, B, and omega. Yeah. So if we go omega squared is equal to 9998.44. Therefore, omega is the square root of that. You can answer somebody. So let's say 1,000 then. What? 100. Yeah, that's right, yeah. Okay, so omega squared, omega is 100. Yeah. Then I omega is equal to 250. Therefore, I is equal to 250 over omega 2.5. Not when you're in the S domain. Any units come back once you go back into the time domain. So the final answer for this, remember, that expression is equal to that expression is the S domain, which doesn't have. When you transfer it back, and then technically the units of omega being added per second also come back. And time is second. Alright? So no, that will only be covered. I won't give you anything that I haven't covered here in these two lessons. Alright? That is a promise. I can guarantee that because I can do that. Yeah. And that's recorded, yeah. Because I know what's in the exam paper tonight. So, yeah. Alright, so what's that? Yeah, but you won't ask to be asked to do that in the series circuit. Alright? You'll only be asked to do that in the same type of circuit as I've already done that, which is the capacitor charging. Yeah? Alright? I'm not going to say any more, right? But you know I'm not going to give you easy route. Yeah? Alright? So, transfer back. I in the time domain is equal to Yeah, that's 2.5 is the constant A, isn't it? E sine close brackets. Yeah, apps. You will lose a mark if you don't put that on the end. Yeah. Technically you can. Technically you can. But you're probably that's unlikely. If we guys, if we graph that expression, that's what we get. Okay, so you can see there's a sine wave there of a fixed frequency, or a repeating waveform of a fixed frequency over time. That's from the sine 100t part of it. Okay, but the amplitude of that sine wave, the number in front of it, is an exponential decay. So what we get is a sine wave decaying over time. And that's what that circuit does. Okay. Now, if I can find a general solution, I might be able to show you how the component values affect that sine wave. But you can end up with, let's go back to my other file, you can end up with, dependent on component values, you can end up with waveforms that don't decay very well. You can end up with waveforms that just do that and finish off if they're tuned properly. Yeah, so depending on component values. So the purpose, one example of a purpose of being able to look into this kind of transforms is in control engineering, where you want a system to run smoothly. If any changes are made, it responds quickly to those changes. So in a system where you've got a pump running at a certain speed and then someone speeds it up from 50% to 75%, you don't want it to do, so as running here, you don't want it to do that. You want it to go from that speed up to that one. Maybe you'll struggle to get no overshoot and undershoot, but that's what you're looking for. Some applications in control engineering, the example I always talk about is the pasteurization of milk. It has to be brought up to a certain temperature, but not go anywhere over that temperature. So this is kind of, would be called underdamped. Yeah, if you can get something like that, critically damped, okay, we have to accept that's going to take longer, and it's overdamped. It takes a long while to get there, but it does overshoot. Please be aware, I ain't going to ask you information for this in the exam. It's to give you a basis of why we're studying Laplace transforms, or one of the reasons we're studying them.